Well, now let's go ahead and talk about how come the Bohr model has quantized energy levels, or discrete energy levels, and therefore discrete photons or colors that come out of it. And this has to do with the wave-like nature of electrons. A fellow by the name of Broglie came along, and he said that there's going to be a wave associated with every particle. I mean, after all, a photon, for example, has wave-like properties and particle-like properties. How come electrons don't? Or any chunk of matter, for that matter, no pun intended. And what he said was the wavelength is going to be inversely proportional to the particle's momentum. Recalling that momentum is equal to mass times velocity, what he's kind of saying, as the momentum goes up, the wavelength is going to go down. And it turns out that most matter is too darn big for us to observe this wavelength because we're dividing by a big number. However, what de Broglie showed was that Bohr orbits exist only when electrons are exhibiting wave-like behaviors and they are constructively interfering with one another. So the electron wave is kind of like a stringed instrument that is resonating at certain frequencies and certain frequencies only. So if we had a positively charged nucleus, and suppose we had a Bohr orbit that lived right here, so that might be my electron as a particle, what de Broglie said was, well, this is actually a wave, and this wave is going to only constructively interfere when these guys line up just right in constructive interference. So there's going to be a certain discrete number of wavelengths that fit together. Something like this wouldn't work out, because when one is going up right here, one is going down, and an electron couldn't live in this orbit. There's going to be ones inside this where it can live, and ones outside here where it can live. But anywhere in between, electrons can't live there because the waves don't match up. So, in essence, when we're looking at the discrete energy levels, we're looking at only where the electron forms a standing wave, and it's going to have a whole number of wavelengths, so an integral number of wavelengths. If the wave does not close on itself, then it's going to be in destructive interference, and that's why electrons can live only in those discrete orbits. So let's go ahead and cut back to my simulation. I've left it where we've exploded our electron. And now we have the de Broglie model. And what you can see is here we're going to have n is equal to 1, n is equal to 2, 3, 4, and so on and so forth. And where the electron hopped into these orbits before, now the wave is going to hop up into those orbits. Everything else from the Bohr model still works out. It can absorb certain colors, it can spit out certain colors, and it can only live where those colors are emitted. Now, I do want to point out that n is equal to 1 is going to have one wavelength, n is equal to 2 is going to have two wavelengths, n is equal to 3 has three, and so on and so forth. And down here we see the same colors that we were seeing before from the Bohr model of the atom. So this kind of leads us into the grand finale for wave-particle duality, and we could be talking about photons, we could be talking about electrons. We can say our old friend c is equal to wavelength times frequency for photons, and we could say v is equal to lambda times f for electrons, because electrons cannot travel at the speed of light because they have some mass associated with them. Photons have, let's just say, no mass. We can definitely say E is equal to h times f for both of these guys. And we could also say that the momentum is equal to Planck's constant divided by the wavelength for any wave or any particle. Let's just go ahead and calculate the wavelength of an electron. The wavelength of an electron should be equal to Planck's constant multiplied by the momentum, and that might be Planck's constant divided by the mass of an electron, which we know, multiplied by the speed of an electron. And if we were to go ahead and look up a typical momentum for an electron, it may be around 7.6 times 10 to the negative 25th kilogram meter per second. We could then say that the wavelength of an electron is going to be equal to Planck's constant, 6.6 times 10 to the negative 34th, divided by the momentum. That's going to be this guy right over there. You type that into your calculator, and you're going to get 8.65 times 10 to the negative 10th meters. And we could also write that as 0.87 nanometers. Now, this is small. This is very small. Again, the wavelength of visible light is going to be 400 to 700 nanometers. The wavelength of electrons are much, much, much smaller than visible light. And what this really means is we can resolve things with electron microscopes, for example, that we cannot resolve with visible light, because you can't essentially see something that has a wavelength smaller than what you're trying to probe it with. So electrons, their small wavelength is actually very useful when it comes to trying to measure very small things. Now, how come we don't see the wave-like property of ordinary everyday objects? Well, it turns out that they're just too darn big. Let's just take, for example, a tennis ball. We could say that the momentum is going to be equal to the mass times the velocity, and if you look up a tennis ball, it's going to have about a 60-gram mass, so 0.06 kilograms, and if we pitched that thing at 100 miles per hour, or 45 meters per second, we can calculate the momentum. 2.7 kilogram meter per second. The de Broglie wavelength would be the Planck's constant multiplied by that momentum, and so we would have 6.6 times 10 to the negative 34th divided by 2.7, and if you type that into your calculator, you're going to get about 2.4 times 10 to the negative 34th meters. That's a small number. That's a very, very, very small number. We don't see the wave-like nature of everyday objects because their wavelength is just too darn small. And if we were to talk about things, objects like you and me and cars and dump trucks, we're not going to see the wave-like nature of them. The wavelength is just too darn big because the wavelength is just too darn small because the momentum is just too darn big. We're dividing by big numbers. Now, I do want to come back after that brief aside into this quantized energy level thing a little bit. And what we saw in my little simulation was the innermost orbit, the n is equal to 1, only had one wavelength. The second orbit had two wavelengths, and this was the n is equal to 2. The third one was going to have 3. This was n is equal to 3, and so on and so forth. So let's go ahead and take a look at this pictorially. I think you can learn a lot more from that. So here's kind of the model of the atom, where we're going to have the positively charged nucleus, and we're going to have n is equal to 1, n is equal to 2, and n is equal to 3. The innermost orbit just had one wavelength. The second one had 2, the third one had 3, and these guys are only going to line up, say right here and right here at certain places, at very discrete places, and that's why each orbit has to be discrete. Anywhere in between, we're going to have destructive interference. We're not going to have whole number multiples of the electron's wavelength. And actually, you're going to build this in the lab, and what you're going to find out is these guys are going to get closer and closer together. Again, we can relate the wavelength to the momentum and to Planck's constant. And something that is kind of interesting is Planck's constant right here is a very fundamental property of atoms. As if Planck's constant were, say, a little bit larger, then what might happen is the wavelength would have to be larger as well. That would make the spacing between atoms quite a bit larger. Conversely, if this was smaller, then this would have to be smaller and atoms would be packed in tighter together. So Planck's constant is a very, very, very fundamental property of atoms. Now, this de Broglie model explains why electrons don't spiral in to the nucleus like the solar system model that I showed you. They're acting like waves, and waves can't spiral in like that. So each electron orbit has to be a standing wave, and it has to have integral number of wavelengths. We can't have standing waves set up kind of in between them. So electrons must have wave-like behavior, and they must have the momentum necessary in order for this to happen. Now, this is all fine and dandy, but I haven't shown you a lot of math yet. Well, it turns out that this fellow by the name of Schrödinger came along, and he came up with this wave equation which describes the wave-like nature of the electrons as they orbit it. As you can see, it looks fairly easy to solve. Actually, it's quite difficult to solve. And the problem with this particular chapter is the math is a little bit complicated. So fortunately, you all don't have to know how to solve this, but I do want you to know that there is some math kind of buried behind all this. But what Schrodinger actually came up with is this little guy right here. And I do want you to know what this little guy is. He actually described this as the probability of finding an electron in some given space. And it did turn out that it has to be a probability because we can't know exactly where the electron is or how fast it's going. We have that minor little thing called Heisenberg's uncertainty principle to worry about. Now, just a little bit more about this little creature called psi. It's kind of like a matter wave amplitude, and it's going to contain all information about the wave. And technically, it's going to have all the information about the particle nature of the wave or the wave-like nature of the wave. And actually, it's going to be some combination of them. Again, there is inherently some uncertainty involved because it could be a particle, or it could be a wave, or it could be here, it could be there, or it could be anywhere. Now, it is only the probability of finding the electron. It turns out we cannot know exactly where the electron is. There's going to be this thing called the uncertainty principle that says we can't know exactly where it is or how fast that it's actually moving. So it actually shows at the end of the day, everything is kind of probabilistic when it comes to finding out where the electron actually is. Now, you may have heard a little bit about this thing called Schrodinger's cat, so let's talk about that. Now, when he described this thing called psi, what he was talking about was, everything to know about a wave or a particle. And it contained all of them until we went ahead and made the measurements. So what he did was he created this scenario where he had this box. And inside of this box, he put his cat. Well, not his cat. It's not a real cat. It's hypothetical. And the cat could be alive or it could be dead. This is like it being a wave or like it being a particle. Because inside of that box, he put in this radioactive, or he put this lethal potion, let's just say, or it would be a lethal gas, and he had something that was radioactive. Now, things that are radioactive, we don't know exactly when it's going to decay. And he had this little detector over here, and when the detector detected some radiation from this, it would drop a hammer and release the poison, and it would kill the cat. The problem is the cat could be both dead or alive until we went ahead and opened the box. This wave function kind of says that the cat is both alive and dead until we open the box. It's a probability. We don't know when the radiation detector, or when the radiation is going to be sent out. We know roughly when it's going to be sent out, but we don't know exactly when. It could be earlier, it could be later. So the cat was both alive and dead, just like the electron could be both a particle and a wave. So this kind of leads us to our progression from having the Bohr model, where we had the positively charged nucleus with the electron whizzing around it, to the wave model, to the Schrodinger model, which is going to kind of combine the two of them. It could be the particle one, it could be the wave one, or it could be both. So now we have some probability space for the electron to kind of live in.